All right. Okay, I'm going to start. So you got my announcement about the test on Monday. We're only doing 2 tests. One, exam 2, and then the very last exam, exam 4. We'll do both of those on campus. So I put in the chat box what it's on. Here also I put what it's on. The cells you were supposed to study that for quiz 2. The organelles, I mean, like, if I say ribosomes, you should know proteins, they make proteins. Or if I say mitochondria, that makes ATP. Just like association, word association. If you know the word association, you should be able to answer the question, because there's not really a lot of ways to answer that. You won't be able to bring your notes, obviously, on Monday, like half of you have been using while you're taking your test. Don't think that I haven't noticed. I've just been not saying anything, but that's going to stop. So having your notes next to you and having your eyes keep looking off to the side, that's over now. So now I'm going to go after you. I'm not going to go after you. I'm just going to submit video of it to the dean, and I'm just going to say, please just let me kick him out. So, and then he'll say, no, don't kick him out. It's just for that. Let me call him in. Then he's going to call you in, and that's going to be like so awkward. So, so that's over. I really want you to study. You should be studying every day. A lot of you are studying every day, and a lot of you are absolutely not studying every day. You're cramming. You're studying right before you take the test. Maybe a lot. Maybe you're studying for 3 hours, and then you're getting pissed. But you can't just take that 3 hours and put it over a week. All right, so this is what it's on. I'm probably going to do another class on Friday that you absolutely don't have to come to, just to talk about this chapter that we're not going to be able to cover today. So I'll cover cell membrane, cell cycle. I won't cover respiration today. I don't have time. I'll do it Friday. Don't feel like you have to come. I'm going to record it, so not a big deal, right? That's just a total optional type of thing. It's not going to hurt you one bit, because I already have a video on this, so it's not going to hurt you. I'm not giving you extra stuff to do. Okay. So let's start talking about the membrane. Really, all right, so I'm going to erase this, because I need the space. If blue's not working and you want me to switch to black, let me know, but blue seems a little darker right now. So the cell membrane is made from, it's also called the phospholipid bilayer. So so I'm going to write that. Meaning it's 2 layers of phospholipids. That's it. So if you remember phospholipids, part of it is you have like the head of the phospholipid that's hydrophilic, meaning that it's water, it mixes with water, and then the tails are hydrophobic. They're essentially fatty acids. They mix with oil or lipids, and it's 2 layers. That's what I call it, bilayer. So like here's the cell. I'm taking like a section of it. Here's all the stuff inside. Nucleus. Here's like the nucleus of the cell. Here's like organelles, all this stuff, whatever this is, right? All this stuff in the cell. And this is all water-based. Here's out of the cell. That's water-based. By the way, we call this extracellular, intracellular, inside, outside. Intracellular, extracellular. So the two, all the heads are facing inside the cell and outside the cell. So it looks something like that. And that, it just keeps going around. And then it's essentially phospholipids just all the way around. That's the membrane of the cell. Of course, I made this membrane really large and quite dramatic. It's not this thick in comparison, but I'm just trying to show you. And then in this are different proteins. So I'm drawing the proteins in black. Like that protein, for example, in black is, I don't know, it's just some kind of gate. So you can see how it'll let things in and out. So it's like a door. I was telling you the other class, I envisioned this like drywall, like a wall. Like this is a door, this is one layer, one drywall. Here's the other drywall on the other side. So this would be like the drywall in the hallway. This would be the drywall in your room. So you got like 2 layers of wall, right? And then you've got like windows and doors, and maybe there's like a sign on your wall, on your door, saying like who that belongs to, who the room belongs to. That would be like a protein. So there's proteins identifying your cells as belonging to you. There's proteins that are like doors that allow things to go in and out. There's other proteins that are like docking stations. So that protein is like a docking station for different things, like you have different things floating out here in the cell. And so you can see like the triangle, I guess that would fit too, but you get what I'm saying. The triangle would fit here, so it's like we call those receptors. So right now, we're really concentrating on the on these membrane proteins that allow things to go in and out of the cell. Because cells are selectively permeable. Meaning that it lets in some things, but other things it doesn't let in. Or it lets out some things, but doesn't let out other things. It controls what goes in and out, which is very critical for our cells to do. First sip of coffee, I had to enjoy it. After this, it's all downhill for me. So really what this lecture is about is how things get in and out of the cell. So phospholipid bilayer, selectively permeable. They'll call it a cell membrane. Sometimes it's called a plasma membrane, which is just kind of the same thing. So that's another name for it, plasma membrane. So if you see either of those names, that's what it is. So how do things get in and out of the cell? I'm going to erase this part here. And remember, it's recording, so if you missed any of it, you can go and find it. So there's 2 ways that things move in our body. And when I'm saying things, I'm talking about like water, gas, like oxygen and carbon dioxide, whatever, sugar, whatever it is that moves around our body. 2 ways that they move across. One is passive, and the other is active. Whenever you see passive and active in biology, it's the difference between them is that one does not use energy, passive does not need any energy, active uses energy. So for active transport, we need energy. We need ATP or we need electrons, some kind of energy source. Passive, it just happens. So first we're going to talk about passive. So things move into the cell or out of the cell passively. And it's a very simple process. It's by diffusion. And diffusion is higher to lower concentration. It's the movement of molecules from an area of higher concentration to an area of lower concentration. It's just higher to lower. Higher to lower density, higher to lower concentration. And it keeps doing that until it reaches an equilibrium. I'm going to erase all this. This is like too much to work with. So let me make my cell smaller. Here's my cell. I'll draw a little nucleus in there. I don't know, that's just what people do sometimes. Okay, here's my substance. I have X's outside of the cell, and I have X's inside of the cell. So, the higher concentration of X's can be found outside of the cell, extracellular. So, we already know which way the X's are going to move. They're going to come into the cell. Because there's more outside than inside. And they'll come into the cell until, that's it, until they're equal. Now they're equal. No more movement. And then the opposite would be true. Right? If there were a lot more X's inside than outside, those X's would move out. Until, so actually we can see exactly how many would move out. In this case, 2. There, now it's equal. And that's it, no more movement. That's diffusion, that's it. It doesn't require energy, it just happens. So, Margaret Orr last night was, she's always going like this and like this and like that. And all she's, I mean, it's way more than this, but really what she's doing is she's taking the H's and she's bringing them to the L's. So if there's a cold front up here and it's like an H, high pressure, and then there's low pressure down where we are, and then she's going to say that this is going to come down here. And so I have no idea about weather, but I mean, that's what it is. It's like a lot of high pressure is going to wherever the low pressure is, because it's passive transport. All right, so weather moves like that. So what makes an airplane fly? Think about the pressure that, like, when you look at an airplane, like, I can't draw shit, but here's like the airplane with like the windows. And like here's the wing right here. So the wing's like coming out, like, so the airplane's flying this way, and here's the wing. So the air going, like the wing's curved, so the air going over the wing is curving, so it's going a lot faster than the air right above it. And so that faster air is a higher pressure, and then the air above the wing is lower pressure. So it like lifts that high pressure going right over the wing, it wants to go to the low pressure, so it like lifts the whole plane. So it's like that kind of, no idea why I said that. So that's it, diffusion. Okay, so sometimes So things move across by diffusion. And sometimes things need help. So we have like regular diffusion, or they'll call it like simple diffusion, and then we have facilitated diffusion. It's still diffusion, but there's some times where things can't just go into the cell. Some things can go in, like, for example, what can use like regular diffusion? Example, oxygen gas, oxygen, carbon dioxide. Sometimes, water can do it. Yeah, those are examples. Small molecules, they can squeeze through. They just squeeze through the phospholipid bilayer. They just squeeze through here and they go in. But sometimes things are too big. So I always think of it like when you go to like a concert or the Superdome or something, you walk through those turnstile things, right? But what about strollers? What about people that are like too large to get to them? What if you have like a whole bus of people come up at the same time? You can't have them go through that, right? So there's like a gate that you open and you let all them through. So that would be facilitated diffusion. So there's some things that need that. So you're helping it. It's still diffusion, but you're helping it. So some examples are ions. Anything with a charge cannot go through by itself. It needs help. So if it's one of those proteins, it's like they call it like a protein channel, or they'll call it a gate. It's just a gate that allows things through. For example, sodium. Sodium goes in and out of your cells. So does potassium. Those are two electrolytes, or two like ions that are constantly going in and out of your cells. And so they're using these gates. All right, so ions will use gates, large molecules. If you want to move a large amount, for example, I don't know if you guys can read that, but there's a protein called an aquaporin. So, aqua, so water. You already know what it is. It's a pore for like water, right? They're aquaporins. They let in and out a lot of water. So if you think about like your kidneys are making urine. They're moving lots of water back and forth. And so they might have like these aquaporins that allow a lot of water to go in and out of your cells. But water can move simple diffusion. If you want to just let a little bit of water, like a slow movement of water in and out. But if you really want to push a bunch at once, then you use facilitated. You have like a special door that they can go through a lot faster to make it go quicker. So these are examples. When you have something with a charge, when you have something that's too large, or when you have a large amount, you want to move a large amount through. And then you use facilitated diffusion. Still diffusion. It's still going to move. It's going to follow what we call a concentration gradient. That's just another way of saying higher to lower. So if I say something follows its concentration gradient, that just means it's going from higher density to lower density. There's a whole volume of research in the social sciences that talks about urinals. Because if you have here's like 5 urinals, right? And so, guys, we already have like the rules set up for this, right? There's 2 urinals that you don't want to use if you're coming in. Well, I mean, you'd probably go over to this furthest one, right? So let's say that there's somebody here already, right? So you can't choose this one, never. And so now you start diffusing, right? You'll use this one or you'll use this one. Probably use that one. The third guy walks in, he's going to go to the middle one. Now the real dilemma is for number 2 and number 4. Right? Do they use this or do they wait? It's acceptable to use this, but if you're the third guy walking in, you can't go to number 4 because that's next to somebody. I don't know. Stupid rules, but there's rules. Right? So, and then, they play around with it and they say, well, what if we add like a 6th urinal? How does that affect the dynamics? What if we put like dividers in between the urinals so you're not actually seeing anyone next to you? It doesn't matter apparently, but it's diffusion. Like everybody, and you do it in an elevator, you just space yourself apart from each other. Or you don't stand like right next to the person. We all space each other out. So we're naturally diffusing. So anyway, concentration gradient, that's another way of saying higher to lower. I'm going to keep this here. All right, that's both of those examples, diffusion and then facilitated diffusion, that's passive transport. That does not require energy. That's how oxygen gets around your body. It's in the air and then we breathe the oxygen in. Well, how does it get into our blood? How does it get into our cells once it's in our blood? Diffusion. Higher to lower pressure. It just keeps moving like that until it gets into our cells.
I have a question.
Yeah.
Is aquaporin a facilitated diffusion, or is that just the way to get a large amount of water out?
It's both. It's an example of facilitated diffusion,
Okay.
but it's for water.
Okay, but nothing else,
Right.
because it's aqua.
Yeah, right, exactly. Yeah, I was just giving you guys an example of moving a large amount of material across a cell. So the other type of movement is active. Active is very simple, it uses energy. Usually, when we talk about energy, most of the time, we mean ATP. So we're using ATP. Why would we want, so we're really talking about pumps. Like, we do this in our life, right? If we talk about the flow of water, so water flows from Lake Pontchartrain into Kenner. You don't have to make the water flood Kenner. They built that on a slump. The water will flood Kenner. And I like to pick on Kenner, I don't know why. New Kenner, I'm talking about New Kenner, Chateau, the end of all of it, Kenner. It's total swamp, and they're like, hey, we're gonna put $600,000 homes here. This is a great place for a really expensive home, and we're gonna make it like 4,000 square feet. Why not? Perfect place for it. Kenner. All right, anyway, water floods Kenner. It naturally happens, but we pump it out. So now you have to take electricity and supply that pump in order to move water, I erased the word, against the concentration gradient. Sometimes you want to move things in the opposite direction of diffusion. So here we have 6 X's on the inside, and we have 6 X's on the outside, and so that's an equilibrium. But we want to take these X's that are on the inside, and we want to put them out. That's going against diffusion. So you're going from like, what, lower to higher? So we pumped them out. And there's different reasons why the body wants to do that, but sometimes the body does that. It pushes things out or it'll push things in. Usually it pushes things out. That's a common thing. So you push things to one side. So that you need energy for that. So you want to use ATP, you want to use an active transport when you're going against, which I already spelled wrong, against the concentration gradient. In other words, you're moving against diffusion. You're going from lower to higher. Just like we do when we pump the water out. It keeps coming in, we have to keep pumping it out. It takes no energy. You don't have to pump water into Canada. It just goes. You have to pump it out. So sometimes our cell will do that. And it does it for a couple of reasons. One reason is that it'll use this idea of diffusion to get things in the cell. Okay, so like let's say I've got like these triangles. Are these trees closed? There's someone else. So we got like these triangles, right? And we want to get these triangles into the cell. These triangles won't naturally go into the cell. So we need to get them inside, but they won't come inside. So what we do is pump out all the X's, and now half of these X's want to come back in. So you pump it out, but they turn around and they come back in again. And so on the way in, these triangles jump on the back of the X's and get a ride into the cell. Whatever, you get what I'm saying. We call that like co-transport, right? So you'll pump something out knowing that it's going to turn around and come back in, but on its way in, you're bringing in something else. Sometimes our cells will take sugar in like this. We'll pump out hydrogen and then or protons, and then the protons come back in, and sugar is like jumping on their backs and getting a ride back in. So that's a reason why. These two ideas, this idea about co-transport, pumping something out, and then something else jumping on its back and riding in, this idea is behind cell respiration. So this is an example of using both. You're using active transport, and then when these X's come back in, that's passive transport. Let me erase this. Got a lot going on here. Shapes. I hope this records right, because it's all backwards when I'm looking at it, but I know you're seeing it normal. But as long as when I end the recording, as long as it's normal, that's fine. All right, so passive transport, active transport. Active uses ATP, or it's some energy source, mostly ATP. Passive, there's two types, regular diffusion and facilitated diffusion. Facilitated just means you're helping it out. Some kind of protein channel or protein gate. If you're taking A&P next semester, you're going to talk a lot about protein, like voltage gated channels. For example, when you study the heart, it's all about that. It's all about these sodium channels. So all this stuff comes back. Okay. Questions on this? If you do, you can just unmute yourself.
Passive does not use energy, that's only active, right?
Only active. All right, so with this idea, let me talk about something else. I'm going to erase this. And let me talk about water. When water goes through diffusion, we have a name for it. Osmosis. Jones. Osmosis is the diffusion of water. But something about water is that it's weird. Water likes to follow solutes. So water does move from a higher to a lower concentration. You know, if there's more water, well, you get it. So, but at the same time, to kind of complicate this, water will follow a solute. And if you remember what a solute is the thing that you're going to put in the liquid. I think when we were using the Kool-Aid example, it was the Kool-Aid powder, the sugar, those were solutes. The water was the solvent. And so the solute was the stuff that's going to be dissolving. There's certain solutes that water really likes to follow, and I'll give you like an example. One is sodium. Na+ is sodium. Water follows sodium. And so, you know, people that have high blood pressure, they'll take medicine to excrete sodium. Like so water pills. Well, water pills. Water pills that people are on, there's two types. One, so now I get to use the word, one type of water pill, they're diuretics, like hydrochlorothiazidol, it opens up aquaporins in the kidneys. Well, aquaporins, if you remember, are like gates for just water, right? So some of those pills open up aquaporins for the kidneys, and then you pee out more water. That's going to lower your blood pressure, because when you pee out more water, you literally have less blood in your body, which, you know, in the case of having high blood pressure, that's what you want. All right, you don't want to be dehydrated, but if you have high blood pressure, then yes, you do want to be dehydrated in that case. Another way is there's ACE inhibitors, and ACE inhibitors ultimately are going to make your body get rid of sodium. So when you pee out sodium, water is going to follow it. So when you get that sodium like into your bladder, ready to go, water is following it that whole way. Water wants to be with sodium. So by getting rid of sodium, you get rid of water. By getting rid of water, you lower your blood volume, which lowers your blood pressure. So, and you'll learn all about that if you're going on to take anatomy. Sodium albumin's another one. That's a protein. Albumin is like egg whites. That's albumin, right? But we have albumin in our body. So we'll use albumin to get fluid in and out of our capillaries. So like here's like a blood capillary, like blood flowing in here. Here's like, I know it's all in blue, but you know, all these red blood cells flowing through our blood vessel. And then we have all this stuff outside, which we call interstitial fluid. I mean, don't worry about it now, but so sometimes you want to get water out of your blood and into the interstitial fluid, or the opposite, right? So we'll use albumin to do that. Like these little dots are albumin. Whenever you make more albumin outside than inside, water wants to go to the albumin. It seems counterintuitive because like this is more crowded, it seems, outside than inside, but that's not how water sees it. It wants to be with albumin. So it goes out to the albumin. So our body manipulates it. If we move albumin into the blood vessel, into the blood, if we put albumin into the blood, then all the water is going to follow the albumin and go into our blood. And vice versa. We can move the albumin out of our blood vessel and all the water will follow it out. All right, so sometimes if people are swelling, like they have too much swelling, you can give them albumin and that'll give them more albumin in their blood and it'll draw some of that water into the blood. But anyway, that's an example of water following solutes. And so what I've been talking about are these two scenarios. One is called hypertonic, and the other one's called hypo. So we have these two words, hyper and hypo. Hyper obviously meaning more, hypo meaning less. Tonic, we're talking about solutes. So I was showing you blood, like you have what's inside the capillary, like the blood vessel, and you have things that are outside the capillary. Right, so I was giving you a comparison. So like when I had this capillary, here's like a blood capillary, and these little dots represent albumin. So there's more dots outside the capillary, and there's fewer dots inside the capillary. So in this case, if we're talking about like albumin, there's more albumin outside the capillary and less albumin inside. So now I've created this environment. Outside is hyper, and inside is hypo. So I say hypotonic, hypertonic. What has more solute? Hypertonic. And if I were to ask you which direction is water going to go, is it going to go into the blood vessel or is it going to go out of the blood vessel? Most of the time, it's the second thing that somebody says when you get a choice between two things. It's usually the second. So if you're a betting person, bet on the second. All right, so it moves out. Water always moves to hypertonic. Whatever has more solute, that's where water wants to be. Think of it, or you can think of it like as like solutes draw water out of things. I mean, it's not really like that, but I mean that's a way to think of it. So if you have so if we have a plant, here's my plant, and it's in a pot. And I'm putting just water in here. So there's my water. Is that even on there? Okay, so if you take the fluid let's start with the water. The water is just water, just plain water. And then you have the fluid that's in the plant, in the roots. Well, it's not pure water. If you take like a plant and get the water out of it, it's not going to be like pure water. There's stuff in that, whatever the plant has. It's water with like some minerals in it and stuff. So in that case, the water that's in the plant is hypertonic because it's got some stuff in it. It's not just pure water. And then the water that you poured into here, it's just water. That's all it is. That's hypotonic. So you're making water go into the plant. Like water wants to go into the roots because that's where there's more solute. If you were to put a bunch of salt in this water, now you've reversed it. You've made more, in here you have salt. So now you're making this hypertonic compared to the roots. You have more solute in the water than you do the roots, and all the water would start to leave the plant like get pulled out. Maybe that's not a good example. I'm like rethinking my example. So, let me try to do one more. So we have two glasses. Here's one glass. Here's another glass. And they're filled with equal amounts of water. All right, and so equal amounts of water. In one, I'm going to put some kind of solute. I'll put like sugar. So they put a couple of sugars. All right. So what happens is that even though there's equal amounts of water, all the water tend to congregate around the sugar. Whereas here, the water is like all spaced out. So even though the dots, I put the same number of dots in both, you know, the amount of water is the same, there's extra space right here. It's like this, we have two classrooms, each with 25 people in it, right? Two equal-sized classrooms, each with 25 people. One of the classrooms, all the people are just sitting in their desks, in their rows, and then the other classroom, you throw in somebody famous. I don't know anyone famous. Someone famous walks in, right? What happens? You all rush that famous person, and because you got to get selfies. Because it didn't happen unless you can document it with a photo. Otherwise, nothing in your life happens. So everyone crowds around this person, right? So now you have a choice of two different classrooms that you can go hang out in for a while. One, you see a classroom, everyone's in every desk. The second classroom also has 25 people, but they're all crowded up on that famous person. So you look at all the desks and they're all empty. So you're like, oh, I'm going to pick that room with the famous person in it. So the famous person's a solute. And the students are like water. So it's kind of, it doesn't make sense. Like, why would water want to be in a jar of sugar water or salt water versus regular water? You think, oh, this is more dense. When you start adding salt to water, it becomes more dense. But that's what water likes, right? So hypertonic, hypotonic. Let me give you like one last example that's like a relevant example, like why you even need to know all this. Let's go back to our blood vessel. Here's our vein. Here's a vein with blood flowing in it. Here's blood cells. And this person is dehydrated, so you need to give them fluids. But your blood is salty. It's around, not that it matters, but it's around 0.9% sodium chloride, salt. So it's got salt in it. So in your cells has 0.9% salt. Outside of your cells has 0.9% salt. It's equal. So it's your blood cells inside and outside are equally salty. We call that iso. Iso meaning kind of like the same. That's isotonic. Your body wants to be isotonic. So your blood inside your red blood cells, outside your red blood cells, like in the plasma, 0.9% salt. So when you go to inject that person and give them like an IV bag, here's like the needle coming in. You don't want to put just water. What if you just did water? We'll just give this person's dehydrated. We're going to give them just water. Okay, so now we're injecting just water in here. So inside the blood cells, 0.9. Outside the blood cells, you're starting to dilute it. You're making it less salty. You're diluting the plasma. You're making it 0.7. So inside's 0.9, outside's 0.7. So one of these now, it's not iso, it's not equal. Out here, outside the cells, you've made it hypotonic compared to inside the cells, hypertonic. So it's 0.9 in here inside your cell, 0.7 outside your cells. So where does the water want to move?
Around the sodium.
Where's more sodium?
In the blood vessels,
In the cells.
in the cell.
So the water wants to go in the cells too, right? And then what happens to the cells when you start shoving all this water in it?
They multiply.
Oh, that would be nice if they did.
They burst.
Break. They start breaking. So if you gave this person just water, you would cause what we call hemolysis, like hemolysis. Hemo meaning blood, lysis, we had that before, meaning break. You're breaking your blood cells, right? That's why you don't give, if you look at IV bags are isotonic. And they'll even say on them zero, most of them, almost all of them, there are some exceptions for different reasons, but 0.9% sodium chloride, because you want it to be what your blood is. You want your blood to be isotonic, you don't want to. But it's possible to die from drinking too much water. And sometimes runners, they do that. They're running like marathons so they can get the sticker for their car. I'm just going to buy the sticker and have all the glory and not do anything. I'll start with the 13.1. I'm not vain. But anyway, you're running the marathon, you're sweating salt, but you keep drinking just water. And since you're running, you're not peeing, because when you pee, you can kind of like make this balance. You drink water, but you can pee the water too. But since you're running, you're not stopping to pee, you're not regulating all of that. And once in a while, somebody will just be running, sweating salt, not peeing, so their blood starts to become, their plasma starts to become hypotonic. It starts to get diluted. It becomes less salty, and inside their blood cells becomes hypertonic. And so the water starts going into their cells, and they break and they die. It's like 1 or 2 people per year. Or they'll do it at a frat party. I don't know why. I don't know what happened to the good old days of drinking themselves into a drunken stupor, but no, they got to do it with regular water now. So they have like water drinking contests. They kill themselves. So, all right. Hypertonic, hypotonic, water always moves towards hypertonic. Osmosis is the diffusion of water. Take this one off there. So you need to know that. We like to be isotonic. Our body's isotonic. We keep stuff, generally, we keep things inside the cell and outside the cell equal. Because we don't want to throw off our body. All right. The last thing on this chapter, all right, the last thing on this chapter is a term called endocytosis and exocytosis. This has nothing to do with water, really. Endo means in, and cyto is always going to tell you something about cell. So if you see the word cyto in a word, C-Y-T-O, it means cell. Endo is going to mean in. And then the opposite of endo, exo. So endocytosis is the cell taking something in. Exocytosis is the cell excreting something, getting rid of something. That's it. So, but there's different types of endocytosis. And so the first one is going to be called phagocytosis. P-H-A-G is going to mean eat. That is in other words. For example, macrophage, phagocyte, esophagus, E-S-O-P-H-A-G-U-S. So that word means to eat. When you see PHAG, get another word. And then, of course, cyto means cell, so it's cell eating. And so, like, here's the cell. I need to draw a little bit bigger for what I want. Here's the cell. The X is what it's going to eat. And then trying to look at another screen so I can see what you're seeing. Then here's like the next picture of it. So you see how it's going to go, right? And then I draw like the next picture of it until the X is inside, right? So it just engulfs it and takes it inside. That's phagocytosis. That's it. There's actually cells that do this. We call them phagocytes. CYT. I can't remember how to spell phagocytes now. Who cares? I got a phone, I can just ask my phone. The other one, cell drinking, penocytosis. It's the same idea, like that drawing that I did for you, it's the same idea, just with liquid, not with molecules. You're not going to really see this, but you will see phagocytosis all the time. That word you're going to see often if you're taking any other classes after this semester. Very common word. And you're going to see this, at least the idea. This is the third type of endocytosis, receptor mediated. I'm going to give you an example. When you go through puberty, you're making more whatever hormones, testosterone or estrogen, progesterone, whatever, right? And that's going to cause some hair growth, right? But you're not growing hair on your eyeball. You're not growing it on your earlobe or the bottom of your feet. You're growing it in certain spots. So why? Why is it that place and not some other place? Why is testosterone, like, why is it going to the testes? Why doesn't it go somewhere else? I mean, it's circulating through your blood. Like, why? Or, well, let's take a better example. Your thyroid gland up in your neck. It uses iodine. It's the only thing pretty much in your body that uses iodine. So when you eat iodine, it's circulating through your whole body. Why isn't that iodine just going to your fingertips and then getting lost? What is it about the thyroid gland? Because the cells of the thyroid gland, there's like your thyroid gland cell, they have these little docking ports that are just for iodine. There's my triangles again. All right, so there's the stuff floating through the blood. Here's the iodine, the triangles, and that's the receptor. So the receptor is a protein that's sitting on top of your cells, and it's designed to catch one thing. So these receptors are going to ignore everything else in your blood, but when the iodine comes by, they're grabbing it. And only the cells of your thyroid gland, they're the only ones that have this receptor. So it's something specific, right? It's when it's important. Most of our cells are looking for particular things. They have particular functions. I don't need testosterone to go to my thyroid gland and I start taking it in. Have aggressive thyroid cells. So That's it. And in all three cases, you're taking something in, eating something, drinking something, something specific. And then exocytosis, of course, I have nothing to put for that. It's just a cell kicking something out. There's not like types of it. It just, that's it. It puts it out. So that is everything. So I'll ask at least a question, at least one question about this on the exam. Honestly, I mean, I'm not going to do it because you guys are going to freak out. But really, what I would like to do is make an essay test. I'm not going to do it, but really, I mean, if you did do it, you would do a lot better. You don't realize it. But all right, so I'm going to do a question on this because really, like an example is I would say, oh, explain the different types of endocytosis. But I know you don't want to like learn the words, and I get it, because that's like, it sucks because you just spend your time memorizing words and you don't. So I'll ask a question on this, at least one, on one of these three, and then I'll just go at least one question on hypertonic versus hypotonic. So remember that water moves towards hypertonic. I might ask you what osmosis is. I'm going to ask you probably a question on, like, you should know when your body would use active transport versus passive. Active versus, no, it's too weird for you guys. Active versus passive transport. So you remember you want to use active when you're going against the concentration gradient. Or another way to say that is going lower to higher. You should know when you would use facilitated diffusion versus simple diffusion. So facilitated, if it's an ion, if it's got a charge, if it's an ion, if it's a large molecule, so something like oxygen, that's simple diffusion. Small molecules, molecules without a charge, gases, oxygen, carbon dioxide, that's simple. All right, the large molecules will use facilitated, and in large quantities. And I gave you the example of an aquaporin. All right, so that's that. Any questions on that? I'm gonna stop recording for a second, and then I'm going to start recording again, and I'm going to break up the lectures. So this whole lecture will have like a theme. So let me
Really quickly.
Yeah.
Endo and exocytosis, those are both examples of what? I guess I understand that it's about taking something in and it's about taking something out.
Endo and exocytosis are both examples of things moving. It's cell transport. So something going into a cell or something going out of a cell.
Okay, perfect.
So I'm stopping this. It's going to go to my